All right, so example 8 is a lot like example 7 and 6 in that it's going to deal with a right triangle, but it has an extra layer of complication for how they're giving you information, and that, of course, is the fact that it's dealing with time passing. So let's go ahead and draw a picture. It says a boat passes a fixed buoy at 9 a.m. heading due west at 3 miles per hour. So we're going to have some sort of right triangle. Our boat is moving due west. Well, I won't put an arrow. I'll just draw a length. Okay. And you can draw yourself a little boat if you want to. And I don't know. I like the arrow. I'm going to label it W for west. And then another boat passes the buoy at 10 a.m. heading due north at 5 miles per hour. So then we have a boat going due north at 5 miles per hour. How fast is the distance between the boats changing? I'm going to use N for north and D for distance, but you could use ABC like Pythagorean theorem. It doesn't matter. Okay, so let's talk about what we know. We know that, let's see, it's due west at 3 miles per hour, so that's its rate. So dW dt equals 3, and I'm going to write miles per hour like as a fraction. We also know that the due north ship is going 5 miles per hour. Well, I'm actually going to put this up here. Okay. And we're working with a right triangle because it's north and west, and they want this distance between them. So we're going to be using Pythagorean theorem. So I'm going to go ahead and just set that up for us. So that would be W squared plus N squared equals D squared. And if we were to do implicit differentiation here, we're going to get 2W times dW dt plus 2N times dN dt equals 2D times dd dt. Okay, so none of that is super alarming, but what is alarming is I feel like I only have 2 values, and yet I have a lot of substitutions I need to make in order to find this dd dt. Okay, so here's where that time aspect comes into play. So we know it's starting at 9 a.m. and we know its rate. So basically that's their kind of like hidden way of telling you how to calculate the actual distance both boats have traveled as well, because we know rate times time gives us distance. So let's take a look at the west ship first. It started at 9 a.m. and it's going 3 miles per hour all the way until 11:30 a.m. So that's happening for what, 2.5 hours? So that means it's traveled a total distance, if you just multiply those, 3 times 2.5, for 7.5 miles. Okay, and then we can do the same approach with the north boat. It's heading, it starts at a little later, so at 10 a.m. versus 9, and it's going 5 miles per hour. So that would only be an hour and a half at 5 miles per hour. So that's going to give us a distance of 7.5 again? Interesting. Okay. Tortoise in the hare, I guess. So now we can, I think we have enough values. Let's try it. So for west, we have 2 times, what? Nope. That's what we just found. So this is essentially your W, and this is essentially, well, yeah, that's the right color. This is not the right color. Boop. Sorry. So this is essentially my W length over here on my triangle. And then the N length essentially is 7.5 as well. So when I come here, I'm going to have 2 times 7.5 miles times my dW dt, which is 3 miles per hour. and then plus, and then my north boat, 2 times 7.5 miles again, times its rate of 5 miles per hour, equals, now, I'm only trying to find the rate changing, the rate that the distance is changing between them. So that's telling me I should actually know this. And this is how it kind of ties back to our previous one. If I know these two particular moments in time are the legs of this triangle, it's also giving me an implied value for that distance between them, right? So essentially what we have over here is a 7.5 squared plus 7.5 squared moment in time. And I can use that to find that particular distance for the value between them. And I'm just going to leave it as a square root of 112.5. I'm not going to actually get a nasty decimal, except it's not C, Miss Right, we use D. Okay. So that's what I'm going to try to squish in over here, because I'm kind of running out of room. But I'm going to put 2 times square root 112.5 times the change in distance over time. And that's just a lot of beautiful work right there. Man. So let's do our best to simplify what's on the left. I have 2 times 7.5, which is 15, plus 2 times 7.5. 2 times 7.5, which is 15, times 3, which is 45. And then that would be miles times miles per hour. So miles squared per hour. I'm just jotting this down so I don't forget it. And then 2 times 7.5 again is 15 times 5. Let's see. And that would give me 75 miles squared per hour. So if I add all of this together, we're going to get 120 miles squared per hour. And I kind of forgot to put our miles with this, but these are in terms of miles, so I'm going to throw that in, times the dt, which is what I'm trying to find. So now I simply just need to divide both sides by this value, and it's going to give us a decimal, not beautiful decimal, but a decimal, of 5.657 approximately, and we're going to divide miles squared per hour by miles, so it'll just leave us with regular miles per hour as what's equal to the change in the distance between the boats versus time. So that's it. That's that answer. And now we just need to write our statement, which I'm going to cheat and just write above because I can't squish anymore on the screen. But the question we were asked is how fast is the distance between the boats changing? We're going to say, so the distance between the boats is increasing because it's positive. At that rate, use your miles per hour, and then say at the specific moment in time it's being asked about.